Okay, now let's look at the magnetic force between two parallel conductors. A current carrying wire creates a magnetic field surrounding the wire. It creates a magnetic field. We've already seen that before. We can find the direction of it with the curl rule, and then we can also find the magnitude of it as we gave the mu naught I over 2 pi r. Now, when another wire is in this field, if I have another wire that's in this field, it experiences a force due to this magnetic field. Because if I have a current carrying wire in a magnetic field, it will experience a force. So when another wire, let's actually clarify this, when another current carrying wire is in the field, it experiences a force. So let me show you. Let's say I have two wires like this. Let's first consider the top wire. It generates a magnetic field. The magnetic field that it generates, found by the curl rule, I let my thumb go in the direction of I, my fingers fold around the wire, and so down here I'm going to have a magnetic field due to wire 1 that is in that direction. All right, so that's my magnetic field, and then I could also calculate the magnitude of that by mu naught I over 2 pi r. Okay, so this is equal to mu naught I over 2 pi r. Now similarly, the current here is going to generate a magnetic field that up here is out of the page. So this wire generates a magnetic field up here. I'll call this B2, which is also equal to mu naught I. In this case, it's mu naught I2 over 2 pi r. And down here, this was due to current 1, mu naught I1. So both of these wires generate a magnetic field. Now, I also know that the force on a current carrying wire in a magnetic field is equal to IL times B. So there is going to be a force on the top wire that is due to the magnetic field B2. That will be F1 due to the magnetic field B2. So this is the force on the wire 1, that's the force on the top wire, due to the magnetic field of the second wire. Similarly, I'm going to have a force here. I'll call this the force on the second wire due to the magnetic field caused by the first wire. Now I can calculate the magnitude of this F12. It's going to be equal to I1, because it's a force on this wire, taking this expression, I1 times L times B, and that's going to be B2, which is going to be mu naught I2 over 2 pi r, which is the magnitude of the magnetic field at this point. And then likewise, because of Newton's third law, I can say that F12 is equal to the negative of F21. So I could actually see that if I wanted to calculate the magnitude of F21, it would look like this. It would be actually very similar, I2 L mu naught I1 over 2 pi r. And you can see that their magnitudes are the same, though their directions are opposite. And this is an implication of Newton's third law. If I have this one force acting on wire 1, I have to have an equal and opposite force acting on wire 2. It also just falls out in how we solve the equations. And this was a similar thing that we saw with Newton's universal law of gravitation, that the forces on two bodies of mass were equal but opposite, regardless of the mass of the objects. And similarly here, even if wire 1 has a much larger current, the two wires are still going to feel the same amount of force, because wire 1 would generate a large magnetic field which would interact, say, with a smaller current in wire 2, but still operate to form the same force on each. Now, if the currents are in opposite directions, do the wires feel an attractive or repulsive force? Well, in this case, they were in the same direction, and we found that they felt an attractive force. So if they were in opposite directions, you should be able to see that they're going to feel opposite forces. Right. I'll leave that to you to try it out, but you can map out the magnetic field due to each of the wires, and then you can determine what is the direction of the force. So you would first have to find the direction of the magnetic field. Well, here, I'll go ahead and do it actually. So let's consider this wire up here. Sorry. Consider this wire. It generates a magnetic field. Let my fingers go in the direction of I. They fold around. And so down here, that magnetic field is in this direction. And now let's just take this scenario. I have this current carrying wire and a magnetic field. What is the direction of the force? Let my fingers go in the direction of I. They fold towards B, which is into the page, which gives us a force that is down. So it's repulsive. Now, we define the ampere based on this force. And the ampere is defined in this way. If two long parallel wires are 1 meter apart, if they carry the same current and experience a force per unit length of this value, then we say that the current equals 1 amp. That's how we define the ampere. We'll come back next time and pick up with the magnetic fields of current loops. In the meantime, though, I also want to just show you this. This is just a simple demonstration of how if you have these two currents flowing and two wires, then you'll find that those two wires are either attracted or repelled. And you can watch this short video here.